Divers can do amazing things, but sometimes things don't go according to plan. The key to diving is to enter the water as streamlined as possible to minimize splash. But why is this? We modeled this phenomenon using a sphere, a box, and an ellipsoid, holding their volumes and densities constant. We dropped these objects from the same height and recorded their entrance into the water.
When an object hits the surface, water is displaced upwards and outwards. The splash contours to the shape of the falling object, ejecting water at 20 to 30 times the impact speed, forming droplet patterns governed by the Reynolds and Webber numbers. Freely moving airborne water droplets result from a high Reynolds number because inertial forces dominate viscous forces. Non-spherical drops result from a high Webber number because inertial forces dominate surface tension. As the object descends, an air cavity is formed beneath. The smaller the surface-to-volume ratio of the object, the greater volume of air the object will pull down. The pressure from the surrounding water causes this cavity to collapse and fill with water, expelling additional water upwards.
In the case of a sphere representing a cannonball, the steep curvature causes a large initial splash, and the small surface area to volume ratio results in the formation of a large spherical air cavity, not ideal for a diver. This entry also causes deceleration due to the significant surface area contact, impacting the water's surface with more total force.
A belly flop, represented by the box, breaks the surface of the water sharply, resulting in a splash that is four-sided, following the contour of the shape. It drags a large air cavity underneath as it submerges, though not as large as the spheres, resulting in additional water rejection. The larger surface area causes the object to decelerate rapidly when it hits the surface, which can be painful for the diver.
Divers aim to enter the water hands first, forming an ellipsoid with their body. The ellipsoid is tapered so that it breaks the surface gently. Less surface area is disrupted, so the initial splash is much smaller. The tapered end also drags a smaller air pocket down along with the ellipsoid. The air pocket is narrow, so small bubbles are pinched off quickly and don't surface all at once, preventing the quick ejection of water. There is almost no resulting splash.
Divers use this property to minimize the splash they create when entering the water.